Building a modern AI model requires massive physical infrastructure. Companies spend billions to string together thousands of high-performance servers, running continuously in vast data centers. But the actual logic driving that hardware is remarkably concise. Computer scientist Andrej Karpathy proved this by writing MicroGPT, a single dependency-free Python file that contains the core logic required to train and run a language model in just 200 lines of code. We often hear these models described as if they are thinking or reasoning. In reality, the core engine operating inside these systems is entirely driven by basic calculus and sequential execution. By looking directly under the hood of this single Python script, we can trace exactly how the data moves. Tracing the variables proves that the system is a piece of legible engineering. To see how this works, we will follow a specific string of data through the code. We will use a simple 4-letter sequence, the name Emma. The system cannot read raw text, so the very first step is the tokenizer. A tokenizer assigns a unique integer to every character in the dataset. Our letters emerge as numbers, 5, 13, 13, and 1, bracketed by a beginning of sequence tag. Yet to the computer, the number 13 holds no inherent meaning, and this sequence provides no context for which M comes first. For the machine to predict what comes next, we have to pass these isolated IDs into the main GPT function. Here, they will be engineered into variables that possess both mathematical identity and chronological time. We start by tracking the integer for the letter E as it hits line 109 of the code, the token embedding layer. This line acts as a lookup table. It takes our simple integer and pulls a dense vector of numbers. This array serves as the token's unique mathematical signature. But without position, EMMA is identical to MAME. Line 110 fixes this with a position embedding, assigning a second vector for its chronological spot. The script then adds these arrays together into a single unified variable named X. This resulting vector successfully encodes both what the letter is and where it lives in time, solving the computer's sequence limitation. We follow the vector X into the multi-head attention block. To predict the future, the model must now look at previous letters to understand context. Here, the variable X is split into 3 distinct smaller arrays through linear transformations. These new vectors are the queries, keys, and values. Processing the second M, the model generates a query asking previous letters. What vowels appeared recently? The earlier E has a key vector matching this query. Their algebraic multiplication is the only place a token communicates with the past. The algorithm then applies a function called softmax. Softmax converts a vector of raw scores into a clean percentage distribution. That percentage determines exactly how much of the E's value vector is passed forward to our current letter M. This entire process is the attention mechanism. It is a token communication system executed through targeted matrix multiplication. Now, we track the context-aware vector out of the attention block and through the final piece of the architecture, a linear layer called the language modeling head. This bar chart shows how the final layer projects the processed vector into a vocabulary-sized space. It generates 27 raw scores, known as logits, for every possible next character in our alphabet. Logits are unnormalized scores representing the model's initial prediction values before conversion into probabilities. A final pass through the softmax function normalizes these raw scores into probabilities, and the bar representing the letter A spikes to the top. The system selects the highest probability. It predicts the next token and finishes the name Emma. We have watched the cycle at the character level, but this scales to modern conversational models. Enterprise AI performs this same loop. It adds embeddings, runs attention matrix multiplications, and calculates logits. We traced 27 characters and 4,000 parameters. The commercial systems process 100,000 sub-word tokens through hundreds of billions of parameters, running on massive GPU clusters. A GPU, or graphics processing unit, is a specialized hardware component capable of performing billions of mathematical calculations in parallel. Generative AI relies on a mechanically consistent process that can be fully understood in just 200 lines of Python.